ground state. So the dominant state becomes the state with 3 bosons in one side and 1 boson in the other side. So this is interesting because this phenomenon is called symmetry breaking, where we just break the symmetry of the state. Here we plot the amplitude before the intersections and after the intersection, and we can see that the amplitude before the intersections are symmetric and after the intersection are antisymmetric. We can use this method in order to identify intersections. We increase again the number of bosons to 6, 8, and 20, and guess what? Here we obtain 6 intersections, 8 intersections, and 20 intersections. Here it's very difficult to see the intersections, but we can use this method to identify the intersection. So, one more. Again, before the intersection, we obtain symmetric amplitude, and after the intersections, we have antisymmetric amplitude. So, this method is very useful in order to identify the intersections. I have only talked about the lowest energy level, but what about the highest energy eigenvalues? Well, we know that the highest energy level is dominated by this state here. This state, in this case, we have 20 bosons, and this state here has the highest amplitude, and it means that we have 20 bosons on just one side and 0 bosons in the other side. But if we play around with Q5, also with Q4 or Q2 here, we can change the composition of the highest energy eigenvalue. And in the last picture here, we see that the highest amplitude is on the state with 10 and 10. It means 10 bosons on each side. So this is also very interesting because we see that we can change the composition of the highest energy eigenvalue just playing with the Q4, Q2, or Q5. In this case, it's only Q5, but it can also be done with Q4 and Q2. So we can